Hello, my name is Kambiz. I'd like to talk to you about the force feedback mechanism. Currently, there is no reliable method to quantitatively assess primary implant stability in the OR. This is important because 75% of hip replacement failures occur due to aseptic loosening. To achieve optimal fixation, a surgeon must know how hard to hit and when to stop impacting. To answer these questions, we developed the force feedback mechanism. This method was derived from the elastic behavior of a bone proxy in our insertion studies. Currently, surgeons apply force haphazardly, assess depth visually, and assess fixation with auditory and tactile senses. We impact as hard as we can to get full seating, trying to avoid loose or tight fixation. However, we typically encounter a polar gap, that is, we can't fully seat the cup. So we choose from one of three options, none of which are sophisticated. We either go for it and get full seating, or crack the acetabulum, or ream and loose press fit fixation, or accept the polar gap. The problem with this approach is that we're applying force and measuring distance, which is an open loop system where the output is not fed back for comparison with the input. In a closed loop system, the output is fed back for comparison. Surgeons intuitively use a qualitative closed loop using their tactile and auditory senses. The question is, how can we have a quantitative closed loop for the press fit process? Press fit arthroplasty is a Goldilocks problem. Too much and you get a fracture, too little and you get aseptic loosening. Majority of fixation occurs at the rim due to harder cortical bone. A simple way to model this is to think of the cavity as two distinct structures with different mechanical properties, the rim and the dome. The rim can be modeled as a stiff spring with elastic properties, which can be calibrated for optimal fixation, where a bigger stretch provides a higher restorative force. In other words, we asked, how do we stretch the acetabular rim just the right amount, but not too much? When we insert a cup into a cavity, we assume the resistive force to insertion is a linear relationship, but this is incorrect because our insertion studies show it to be an exponential-like curve. With increasing energy, cup insertion and extraction force increase linearly, then non-linearly, and then a plateau. In this nonlinear zone, 90% of cup insertion and 90% extraction force are achieved, with only 50% of total energy required for full insertion. This implies that the nonlinear zone may be a better endpoint than full seating, which begs the question, why apply 4 kilonewtons of force and risk fracture to get the final 10%? We can find this nonlinear zone using two metrics we've named as the force and rate of insertion footprints. When you insert a cup into a cavity with a given energy, you will see a cup insertion profile over a certain number of impacts. This produces the measured force profile in bone. The first and second order relationships of measured force profile as a function of number of impacts to seating produce the force and rate of insertion footprints. This phenomena is observable because the two collisions that occur are mechanically different. The proximal is always elastic, the distal collision always inelastic, becoming elastic over repeated impacts. The distal collision always goes from compliance to non-compliance, which produces the profiles, which in turn produce the footprints. Tracking the two footprints allows you to monitor incremental cup insertion, so you know when you have reached the nonlinear zone and have reached best fixation short of fracture. That is, if you deliver impact energy incrementally, you can measure and track the force and rate of insertion footprints. When the force footprint plateaus, the chosen energy is not inserting anymore, nor are you getting any more extraction force. You can increase impact energy to the next level. The rate of insertion footprint, on the other hand, provides an indication of the elastic capacity of the rim, which helps you decide when to stop impacting. This provides the foundation for the fixation algorithm, where incremental cup displacement can be monitored through measured force in bone, tool, or at the interface. This is now a closed-loop system, where the output is fed back for comparison to allow adjustments of energy for desired fixation. Competing concepts are still open-loop because their outputs, measured vibrations or impulse, are not fed back for comparison with the input. Thus, there can be no modulation of impact energy for the desired fixation. Ultimately, the force feedback mechanism is a system that learns as it interacts with an unknown environment and modulates application of force to obtain optimal implant stability. Additionally, this is a method with potential for integration of cognitive technologies.